And then this will be minus x, and now these will both be plus x. So this line will be 2 minus x, x, and x. And because the Ka is 1.8 times 10 to the negative fifth, what are we allowed to do? Ignore the fact that it is minus x. So 1.8 times 10 to the negative 5 equals x squared over 2. And then you solve for x. And why do we want to know x? Because x gives us concentration of H plus at equilibrium, and then you can do what? Yeah, take the negative log of that, and that will give you the pH. Barry.
Why could you cancel out that
Because this number is so small that is this going to dissociate very much? It's only going to dissociate a little bit. So 2 minus a tiny bit is still going to be about what?
2.
About 2. So you guys should have your calculators out. Should be doing this one.
There it is. Oh my gosh, thank goodness.
What did you get for the H plus concentration? 0.006, that's what I got 2. And then what do you do?
And then negative.
What is it doing?
Take the negative log of 0.006, and you should get, first of all, how many significant figures is this? 2. How many is this? 2. Neither of these are pH. pH is the only weird one, or POH.
Okay.
So then your pH needs 2 decimal places, so what's the answer? 2.22. 2.22. So then what would POH be? Wait, what? So pH equals 2.22. So what does POH equal? 11.78. And then what does OH minus equal?
To the 10.
Sheldon, what did you get for N?
0.006. Did you do 1.8 times 10 to the negative times 2? And then take the square root of it?
Put it in the next solve, but look at it.
Yeah, we always do that.
And then what did you get for OH minus concentration? 1.7 times 10 to the negative 12? Molar? Yes? Oh, maybe if I put in, I just put in 11.78.
I got the right answer now.
You got it? Everybody good with that one? You sure? Okay.
Wait, what'd you get for OH minus?
Okay, wait. OH minus, I got 1.7 times 10 to the negative 12 molar. 10 to the negative 11.78.
Oh. And the H plus is just the...
The H plus is whatever you get for X there. And I got 0.006. So another way to do it is 1 times 10 to the negative 14th divided by 0.006. Should still give you about 1.7 times 10 to the negative 12.
Yeah.
Are we good with that one? Okay, I'm going to reset. Move on. I don't know what I just did. Okay, so what if you have a mixture of weak acids? Just like, so processes, you're going to be doing the same exact thing. You're still doing an ice table. Usually you only have to do the calculations for one of the 2 acids because only one of them is actually the one that's going to contribute more H plus than the other. But if they're both similar in their Ka values, then you pretty much have to do how much is contributed by this weak acid and then how much is contributed by this weak acid, and then add the H plus concentrations together and then find the negative log of that. So if you have one that is more concentrated or with a much greater Ka value, then you don't even need to do any of the calculations for the other one. But if they're like similar concentrations and similar Ka values, like for example, if they were like, that would be a weird one, but if it was like a combination of HF and HNO2, and they were both the same exact concentration, you'd have to do 2 ice tables and add the H pluses together. So that's what I was saying there. So here's one. And look, I picked HCN and HNO2, so that's nicer. So you've got 1 molar HCN and 5 molar HNO2. So to find the pH, which one of those is really going to be the one that's going to affect the pH? HNO2. This HCN, is it going to contribute any H plus at all? Is it going to contribute any H plus ions at all?
Yeah.
Yeah, it's an acid, it will still contribute some, but the number is going to be so small that you get from that, that if you added it to this one, it's still going to be almost the same exact number. So I want you to actually calculate it just for HNO2. I'm going to do a work up here for HCN, and you'll see how small of a number we get for H plus. So to find the pH, so for you guys, find the pH of 5 molar HNO2. I'm going to up here on the board find the pH, or find the H plus that's, just find the H plus. Don't find the pH, just find the H plus that is contributed by 5 molar HNO2. I'm going to do the same thing if I'm going to do the HCN.
So we're doing the HNO2.
Yep, you're doing the HNO2 because I'm going to show you why you don't really have to even include this HCN. Yeah.
For like all the Ka values, are they considered all like really small, so you don't even, like for anyone, you don't.
No, some of them that are weird are some of the polyprotics that I'll talk about later, and chlorous acid is not that small, but that one doesn't usually come up very often.
But like for this one, we don't have to do like 5 days eggs. We can just do 5.
Yeah, you can always ignore it. For your purposes, always ignore it, and then I'm going to show you something you're going to have to do to check to see if you're really allowed to do that. Did you guys get the H plus concentration yet? You're still working on it. I picked a different problem.
Hey, can we quiz Noah on what happens in the class tomorrow, see if he actually watches it?
Sure.
Because there are some embedded messages in there too, so let's see.
Okay, did you guys get that the H plus concentration is 0.045?
Yes.
Yeah.
Okay, I did it for HCN, and I got that the H plus concentration is 2.5 times 10 to the negative fifth. So if you add these two numbers together, what are you gonna get? About 0.045, right? And then, how do you find the pH now? Take the negative log of this. So the acid that's much, much, much weaker and usually more dilute won't even contribute. If you really just want to do both of them, then you can do 2 different ice tables, and what you do is you say the H plus contributed by this acid plus the H plus contributed by this acid will all be there in solution together, and that's what will give you the pH. But I'm going to add those two together and show you that you're going to get the same thing. 0.045 plus 2.5 times 10 to the negative 5. I have still 0.04525. So it doesn't change anything. So you can ignore the second acid if it is less concentrated or if it has a much lower Ka value. So then what's the pH going to be? Okay, with sig figs, what is it going to be? I got 1.35. 1.35. Are we all good with that? Okay. Good. All right. So then I think the last thing that I want to talk about before we do some problems is percent dissociation. So you have to be able to calculate how much of it dissociates, which is actually not a difficult problem. This is the easy part. If you can handle all this, percent dissociation is easy. So percent dissociate is the amount of it that dissociates over the initial concentration, which means X over the initial concentration. That's it. And if it is greater than 5, then you are not allowed to ignore this minus X. I don't think I've ever seen it ever be greater than 5 in any of these problems. So here's one. Here's a problem. So it's actually 2 different problems. Calculate the percent dissociation of 1 molar acetic acid, and then calculate the percent dissociation of 0.1 molar. So 2 different problems, and the reason I want you to do those is because you can't memorize what the percent dissociation is for an acid. It will change with its molarity. So what do you still have to do? Yeah, you still have to do it. Morning, Cameron. It doesn't look like chemistry. Not doing chemistry.
Yeah, if you want to give a message to Noah, he's in there.
Okay, so what did you get? Did you guys get this for 1 molar? 0.42% dissociated? Yes. All right. So 1 molar is 0.42% dissociated. Now we're going to do 0.1 molar. So that just changes this to 0.1. 0.1. You got that?
I just,
Michelle looks over real quick to get a selfie.
Miss Jill, how do you know the amount dissociated?
It's X.
Look directly.
Because it's like how much actually dissociated is X. So for 0.1 molar, how much? What did you find X to be? 0.0013. So percent dissociation is 0.13%. Is that right? I did it wrong.
Because you got 2 things, you get 1 more.
Oh my gosh, I didn't divide by 0.1. Oh, is that what you just said to me? 1.3%. So 1.3%. I was like, why did that answer not what I expected to be? Okay, so can you handle the percent dissociation? You notice something? What happened as the molarity went down? More dissociated. Why would that be true? And so you need to write it down. For weak acids, because for strong acids, what do we say about percent dissociation? It's always 100%. But for weak acid, percent dissociation increases as the acid becomes more dilute. Maybe you think they could attempt to explain that one. It's kind of weird. Maybe you think they have an idea?
This is like water with the H plus ions increase the concentration.
Okay, so there's H plus ions that are already there because of the water. Okay. Yes, all right. And this is a hint here. You don't have to look in your book. You can write down that page if you want to look at it later. But there's a hint there, so I think they can explain it based on that. I'm gonna move this so it's on the. I don't want you to do that. All right, this one's the one on your phone right now. Anybody think they can? No hint from there from last chapter? Do you even know what I'm asking? Okay, why is it gonna shift? Okay. So you're not adding any more water. So it's like you've got water in there, and so water already has H plus in there. It doesn't have any A minus in there at all. Okay? There's no A minus in there. But so when you put an acid, the more concentrated this acid